Hi and welcome to our today's webinar. We will speak about our new universal testing platform TCM, and I'm Manfred Maskos. I'm the responsible product manager for this product. And for your information, if you have any questions during the webinar, you can write them in the Q&A and then we will answer them afterwards, because we have too many people joining the webinar. It would be too confusing if we answer them directly. So thank you for joining, and we will start directly with our overview. Okay, so firstly we will have a look on who is FOERSTER. So FOERSTER was founded in 1948 by Friedrich Foerster in Reutlingen, and he started the base of the technology FOERSTER is still using today. For sure, in the former times we continued developing and increasing our technology over time, but the base of our technology was really founded in 1948. Now FOERSTER changed. FOERSTER has now 650 employees worldwide, and we have a revenue annual of around 120 million. So FOERSTER was really internationalized and is active internationally with many subsidiaries. So we have 9 subsidiaries over the world, and we have many partners in over 60 countries. So we have a huge service network over the world. So everywhere in the world you can get in touch with our experts to discuss your NDT testing task. FOERSTER in Germany is active in different business units, and we try to cover the production process from the beginning to the end. So we start with the semi-finished products with our business unit TS, and this business unit is focused on testing endless products like bars, rods, and tubes. Then it's our division component testing. These colleagues are working on automated test systems and really focus on testing like practice, camshafts, and other single components which are safety critical in cars or parts for aviation industry or other segments. Then we have an inspection team for reformer tube testing, and they go directly to the chemical plants and do the testing on site, on customer side. And our division DS for detection and security. This division produces and organizes the production of mine detectors, as example, and other detection systems, especially for the military. And the business unit I'm coming from, so the mobile testing, we look at products which are used in mobile testing and try to offer solutions for your testing task. That's all about FOERSTER for today. So I will also not talk about the eddy current testing principle and basics, because we have a YouTube video online. So if you like to know more about eddy current testing in detail, you can have a look on our website, on our YouTube channel. FOERSTER has a huge amount of experience in eddy current testing, especially for inline products. So we have a huge amount of inline products for component testing, for semi-finished product testing, and so on. So we have a huge experience in that area. Additionally, we have huge experience in mobile testing with the defectometer, which is a very easy, quick testing instrument, and the Sigma test, which is a conductivity meter for conductivity measurement. And in former times, we had defectometer and defectoscope, and a defectoscope was out of market around 13 years now, but we still have this experience, especially in our probe construction and probe production. Yeah, and what happens if we put everything of that together in one product? Yeah, at the end, nothing, because we can have a huge amount of experience, but we need your help to develop a good product. We need the help of our customers, and from you, we got the feedback such a universal eddy current test instrument should be lightweight, should be very small, should be durable, should have a large screen, should be usable with gloves, should be sunlight readable, should have a battery time over 6 hours, should work on a operating system which is commonly used for easy data transfer, should have a good signal quality for sure. For good testing, you need good signal quality, and it should be on a good price. And there it is. So we have a weight of 1.3 kilogram with our system. We have dimensions which are really small compared to other instruments in the market. We have a drop height of 1.5 meter, so it's really durable, the whole system. It can be used with gloves. We have a screen size of 8-inch, and we have a brightness scale of 800 nits, so it's very good readable in the sunlight. We have a battery time of over 6 hours. We have a basic operating system in the background, which is Windows. So it is very easy to put the instrument in a network or to transfer data to other computers. We have the FOERSTER signal quality in this instrument. So that means we put our experience from inline instruments and other instruments in this development, and we now reached really a signal quality which is comparable with our inline systems, comparable or maybe also sometimes better. And we have really a valuable price on it. So, okay, TCM is not only an eddy current test instrument, we try to build up really a platform for eddy current testing to solve any eddy current testing task. Sure, actually we start with the basics, but it will continue. So actually we start with de facto scope, which is the standard universal testing, which you know from also other instruments, but sure with the FOERSTER signal quality and other advantages we will see later. We have the conductivity measurement with a sigma test, which is a module on it. And we have the eddy current error testing, which will be launched Q1 next year. And for sure, we are still working to continue this, and we are working on more and more modules for this instrument to cover multiple applications in future. TCM is at the end the follow-up of the de facto scope SD and defectometer 2.837. So really old but really stable instruments, and these instruments already covered a huge amount of applications. And TCM is now compatible with all of these sensors and even more. So we are compatible with the parametric sensors of defectometer, with transformatoric sensors like absolute or differential probes, which are used in automated testing or also on several mobile testing tasks. We can connect bridge probes, which are used very often in the US. And we can also connect a huge variety of competitors' probes. So if you have a huge amount of probes from your testing tasks on site, no problem, we can offer the fitting adapters and you can still use these probes. Okay, we talked enough for the first step. Let's have a look on the instrument itself. So we will start to unbox it. We have the instrument in that case. So it comes in this really robust case. Everything is really good protected and we can open it really easy. And there it is. So on this side we have the cables in it. So we can open it and we get the cables out of it. I put only one cable in it because it's actually easier for this webinar, but there's a huge amount of space for additional equipment. Okay, top.
Sure.
So, okay, then we have two layers in this box. So the upper layer, we have the instrument, and on the lower layer, we have other equipments, like we have actually the hand strap here, we have some space for a spare battery, and there we have some holder for standards we can mount on the instrument. We can also have a look later, and that is the two-layer principle to have really enough space for your equipment. I will put this away. Okay, and there we have the instrument itself. We have some probes in it here. So we have some ring probes, we have some transmission probe, and there we have a rotating probe we use later on, and the rotating head. And we have on the side here a low frequency probe we will also use for applications later. The instrument itself, we see here the three applications we also saw in the presentation. On the side, we have here the connections of two USB-C and Thunderbolt 4. So we have capabilities to transfer a huge amount of data really fast. We have on this side, we have the fast charging input, so we can really make a fast charging of the instrument, and we can also load the instrument over the USB-C, but it's a bit slower. Then we have here the probe connector. It's a LEMO 19-pin connector, so really standard. And with this connector, we do every connection to any sensor or encoder. Then we have here, we can clap out a stand, so we can place the instrument very stable on the table. And we have some connection point here, where we can connect our hand strap. So I can move the hand strap on it, and I can hold the instrument very good in the hand, and I can rotate it in this position where I like to use it. So if I like it to use perpendicular, I can use it like that, or horizontal, and this direction. So I'm completely free in the position I'm testing. I can delete it. And on this side, there we have the battery. The battery can be swapped. We only can remove this and this one, and we can remove the battery and put a new into it and continue with testing. On the bottom side, we have the connection of for the docking station. So also huge amount of connectivity is possible. For our webinar, I prepared a docking station, a standard docking station, and I will connect the instrument with the docking station, and we will have the screen shown in very high resolution in the presentation for later tasks. Okay, so let's move it here, and we will continue with the presentation. Okay, so we will start with the borehole inspection with rotating probes. So borehole inspection is, here we put the probe in the borehole, rotate it, and we get a scan of one line. And if there's a crack, we get a signal indication of this crack, and we can sort this area out where we can detect this crack, and we know, okay, this part is bad. If we like to scan the whole borehole for cracks, so not only one small area, we can make that with a rotating probe. So we have a probe which is connected to a rotary head, and this rotary head rotates the probe with around 2000 RPM. And now we can scan with this rotating probe the whole area of this borehole, and we can get a complete eddy current picture of this borehole, and we see directly where the crack is, and see the crack really, really good in this this image. Okay, let's have a look on this application in live. Right, we have our connection cable, so I will connect it to our instrument. And we have our rotating head, and I connect it here with the cable. Oops. Then we have our rotating probe, which we put in the rotating head, and this rotating probe needs to fit the borehole we like to test later. So, okay, fits in. And then we go to defectoscope. And there we have, oh, I forgot on the last webinar to switch to English language. So we go back and shortly we switch to the English language. English, home, defectoscope. We can go to rotary test. So we prepared some programs. Rotary test, start. Okay, and now we have the possibility to go with auto set. Choose rotating probe. And there we have a probe diameter. On the probe it's standing, we have probe diameter of 8 millimeters. And it says, after that, please start rotation and click next. So we start the rotation of the rotating probe and click next. And it automatically calculated the filters, and we can start with testing. So we scan, we scan the borehole. There is a crack, and I can freeze the signal and increase the gain till this crack reaches the threshold. Okay. And now I'm ready for scanning. Sure, this is the standard eddy current signal. And we can also go to chart, C-scan, and then we already have the C-scan. I will click this, and we can scan. And we have a nice C-scan of the whole borehole. And we also directly see, okay, our scan started in this area, it ended in this area, so the crack is in the middle of the borehole, and we really know the position of the crack. Yeah, so that's it firstly for about the rotating test, and we will continue with the presentation. So the next step is how to detect smallest cracks. So what is the limitation of crack testing when using the TCM defectoscope? In this picture we see we have a spring-loaded probe, so a standard pencil probe which is loaded with a spring. We will also see it live. And we have a 100 micrometer deep crack in this tube, and we scan this tube and see the indication of the 100 micron crack. For this application, it's necessary to have a really low surface roughness to get a good crack indication. Another application we will have a look at is a semi-automated test. We fix the test part in the drilling machine to have really a good positioning and rotate the part. And then we can really get also really small cracks as a signal. So we can really test for cracks which only have a depth of 30 microns. Okay, and this we'll also look at live. I will remove the rotating probe, and we will take this part. I will connect the correct probe. So this now is a standard probe which was used in former times with the defectometer M. We load a program which I made before. So I prepared this 100 micron detection program. Okay. And there we are. It's already running. Can put the probe on the material. You see here, it's really a standard pencil probe and a guidance with the spring loaded. So it's mounted here, and we have a constant pressure with the probe on the material, and I'm very good at scanning. So I make 0 on the material, and we can start scanning, and there we see the crack comes really nice as a signal. Again, 0. Okay. And to get a feeling how much the signal is, if we scan over a crack which is 0.5 millimeter depth, it really comes out of the scale. So it's really a very small crack indication we can show here with the instrument. Okay. Then we will switch to the semi-automated test. So I have a small rotation station. Okay. And I will disconnect the probe itself. Get this back again. Okay, and then I will load the program I prepared for this one. So it is 30 micron scanning program. Okay, I will start the rotation. So this cylinder is then rotating. So you see if I move it with hand, we directly see already the cracks very good. Normally you scan such things with a higher speed, so we can increase it. So and we get a very high speed. Yeah, and with that we can make a scan over the surface. So if I move the probe up, we have a surface area without a crack, so we have no signal from the material. And if I move down, we see the crack signals, and this signal here is a crack with a 50 micrometer depth, and this crack is 30 micrometer depth. So really small cracks we can show very clear with the instrument. Okay, let's get back to the presentation. Sorry. Okay, the next one we will have a look at is the residual wall inspection. So that means we have a probe which we use at a very low test frequency to penetrate really deep in the material, through the material, to check if the material thickness is still the same as we would expect. And for that inspection task, we have a standard, which is, here I have a closer look, which has a residual wall loss of 10%, 20%, and 30%. You see here, this residual wall loss you nearly don't see in the camera. And there we have 20% and 30% residual wall loss. And yeah, this we will also look at live. I will switch to the correct probe. One moment. Okay, so for that we will use a low frequency testing probe. So this probe is optimized to test at 2 kilohertz, but you can also use it on other test frequencies. We will load the program I prepared for that. So we have low frequency residual wall testing. And we put the probe on the material, make 0. And then we have now the liftoff effect if I'm moving the probe. And we can make this liftoff very fast in one direction. We press one time on phase, and it's directly moved in this direction. If we like to move the phase manually, I can freeze the signal. So I move the probe and I freeze the signal. And now I can move the signal by touching it on the screen and doing that manually. Or I can move it with the parameters directly here. Okay, and then we start with the testing. So there we have 10% residual. So yes, I moved too much. We have 10% residual wall loss, 20 and 30. So we have really clear signal indications of that. And this probe is optimized to have a very low edge effect, so we can go very close to the edge and we don't get really high effects from that. Okay, Let's go to the presentation. The next testing task we will have a look at, it's also the last for the vector scope, is the multi-frequency testing. And when we do multi-frequency testing, we can use the probe for different kind of applications parallel. So that means we make a setup that this probe we used before is optimized for the residual wall testing, and we additional do a setup where it is optimized to test for cracks. So we can parallel crack for residual wall and for small surface cracks. And that we will also have a look at live. And we load again a program for that. Tool frequency testing I prepared before, and see everything is very similar as we had it before. And now I put the probe on the material, and we see two signal lines. One is white and one is bright blue. And I do a 0, and we can scan over the surface, and we see one signal is increasing when I move over these cracks. And it is the white signal, and the white signal is frequency 1. You see here, frequency 1 is 300 kilohertz, so very high frequency. And we do a crack testing with a high frequency. If we do the same on the residual wall standard material, I can see it because this material is a bit different. We scan, we see only the blue signal is moving. So we know, okay, there we have a residual wall loss. The second frequency we use has 2 kilohertz. And yeah, we can really make a test parallel for cracks and residual wall, and also consider and also decide, okay, this was a crack and this was a residual wall loss in parallel. Okay. That's for now all about the applications for the vector scope. If you have afterwards some questions about that, write it in the Q&A, and we will have a look at it afterwards. And now we will continue with sigma test. So sigma test is an application for measuring the electrical conductivity of non-ferrous material. And for that we use calibrated probes of our sigma test 2070, which is really known in the market with the highest measurement accuracy, and shielded probes. So the probes are so good shielded that you can really measure directly on the material's edges and do not have an effect of this on the measurement. And very important for measuring the electrical conductivity, we fulfill the standard national standards, and yeah, that's very important for a measurement system. Let's have a look on the adjustment of the system. So for the adjustment, we can click on the adjustment and set up the values of the calibration block, because for electrical conductivity measurement, we always need a calibration block. And for TCM sigma test, we always need a copper calibration block, a minimum. Then we do the measurement on this block, and our system is already adjusted. This we will also have a look live later. One moment. The second thing we will have a look at is the visualization. So we have the possibility to visualize the measurements on separate values, or we can also have a look at it in the stream with up to 5,000 measurements per second. So we can really make a conductivity scan. And this we will have a look at now live. Okay. So I connect a sigma test probe. It's really a standard probe of our common sigma test 2070 with the correct adapter cable. And now you saw the sigma test app gets active because the instrument recognized, okay, this probe was connected now. We go into sigma test, and we can now go to adjustment, and there we already prepared the values which are written on the standard, And if you like to change these values because you have a different standard, you can swipe right or left. Right swipe is to delete the value, or left swipe is to edit the value. So we go on our standard, click next, put the probe, we put the probe on the copper material, click measure. Okay, measurement done. Next standard, put it on the other one, measure, and done. Okay, so, someone set up the continuous mode before, so we will start with touch mode. On touch mode, it automatically reduces the sampling rate because then it's better to use. And now we can control our standards, okay, 59.39 and 4.28, so exactly the values we set up before. And here we can do single measurements on the material and see a bulk. The signal is displayed here, and if we like to see, okay, what was, as example, this red one, we can press on it, and okay, it was the 30s measurement, and it had the value of 59.39. Yeah, I set up a threshold to sort out values above 23 megasiemens per meter, so that's correct. If we like to switch to another unit, as example, instead of megasiemens per meter percentage ISCS, I press on this and I can directly choose between the different units. And always, if I do that, this unit is completely set up in the background, so you don't need to search in some menu to switch these units. Now, before I talked about that we are able to do an eddy current and a conductivity scan, and for that we can go to continuous and switch the chart. And there we already have now a chart, yeah, where we can have a scan, but it's not really fluent. Here you see it's not very fast. And to make it faster, we can go to advanced functions and we can increase the sampling rate to, as example, 500. Close. Okay, and now we can really do a fast scan. You see we have 500 samples per second, and we can make really a conductivity scan of the surface. Okay. Then let's continue with the presentation. To get really a technical overview about the conductivity measurement, there are some differences comparing the sigma test 2070 and the TCM sigma test. So the sigma test 2070 has additional distance compensation of the signal to measure through the paintings. It can operate up to 160 kilohertz. We have there an additional 5mm probe, and as a standalone solution, it has a lower price. So if you only need a conductivity meter, it's always better to go directly to a sigma test 2070. If you need a combined instrument, if you're doing several testing tasks and switch between them, then a TCM sigma test is a very good solution. Now we directly move to eddy current array testing. The eddy current array inspection solves at the end all applications which are also possible with de facto scope, but with a higher number of probes. So if you make a scan, as example, with a 1.5mm probe and scan line by line, with array you can make up to 512 probe elements in parallel and do one scan, and it's much faster and safer to test with such array probe. The array software will have the same user experience as for non-array inspection, so there is no additional training necessary to do eddy current array testing. If you are able to do standard eddy current array testing, you are also able to do array testing. And the documentation will be possible with a high-resolution C-scan, so it's very nice to save the whole eddy current signal as an image. And for sure, the probes have a chip on it, and all probe data are saved on this chip. So everything which is very more complicated, is set up completely in the background. Yeah, and for you as overflow, the array probes at the end are really the same as if you put multiple separate probes together and use them for a scan. Sure, there are additional variants available which combine such probes, but this is the standard. And we will start with a 24-channel array probe for low frequency testing with a 6mm track width for each probe and with a 140mm scan width. And additional, we will have a 64-channel array probe for high-resolution crack detection with a 1.5mm track width and a scan width of 96mm. Yeah, and at the end, there would be a possibility to build up probes up to 512 channels, probes, but as more channels probes you have, as slower your testing gets. So we got the 64 channels as a really good value for that. This all is coming in Q1 next year, so it will take a short time. Actually, we are really focused on this development. So if you have specific tasks for eddy current array testing, you can contact us and we can discuss, okay, how to solve your application. Maybe this probe already fits to your application, maybe not. So we should have a discussion, what exactly is your testing task. Now let's have a look on the embedded help of the instrument. So everywhere in the software, there's such information button, such info button. And if you press on this info button, it shows all information which relates to this dialog. So as example, if you press the info button in home screen, it shows, okay, you are in home screen, you are using an eddy current instrument, test instrument. You have now the possibilities to go into vectorscope, sigma test, and so on. So the whole description of this dialog. This goes even deeper if you are in a parameter like the test frequency. So there this described in detail, okay, what is the test frequency, what you change with it if you switch it, and what effect you have on the penetration depth of the eddy current signal. And additionally, you get the information what you can do additional with this parameter. You can do a two-frequency testing, mixing, and so on. Everything is described here. And for some parameters like the gain, there's also an animation. And this we will also look at on the instrument on site. So, thank you. So if I go here on the information button, you see the information of the home screen. But more interesting it is if you are going, you see this this documentation bar as example here. There's an information button, and this describes now, okay, what each symbol means, what you can do with it, and you don't have to read the manual. Everything is described directly in the instrument. And additionally, as example in frequency, there's also the info button. You see here the whole text dialog with some descriptions. And also in the phase, as example, that we have also some animations which describes how to use it and also when to use the phase. Then we saw on the screen the information and documentation bar, and with this bar you can make screenshots, reports, and you can also additionally record raw data. And that means you can start the recording and save this raw data on the hard disk or USB file. The hard disk has 128 GB, so you have huge amount of space to do eddy current recordings. And when you did a recording, you have afterwards the possibility to make a post-processing. And that you start in system with the demo mode. So you disconnect from the hardware of the system, and then you can go normally in the program go to load recorded stream, and then you can load this data to look at it. And this data you can load as a still image, or you can also load them as a continuously stream that you completely see how the operator moved the probe, was tilting with the probe, and everything around. So you have really a deep view into the eddy current signal. And this post-processing can also be done on your office laptop or computer. You can install this software of TCM on any Windows computer, and this installation is for free. So with any TCM instrument, the software comes for free, and you can install it on all of your office laptops and do your documentation or data evaluation afterwards and have a look at it. More information you will find on our website of the TCM. So there is the data sheet, some descriptions, and we will also provide in future some videos, show some for promotions, and also some videos about applications, how to use it, how to make a rotary test, how to do it in wall testing, and other applications like how to use the documentation